What?
That 30 seconds I was in that major. That was a rough time.
Oh. You said, excuse me. Okay. All right. Let me see. You good? Okay. Okay. All right. What I want to do today is I want to start into the realm of bridge engineering. And I sort of debated how I want to do that. Where you all have an alternatives phase coming up, I figure one of the first things that we need to do is we need to start talking about some preliminary sizing. So what I have here is a sort of a brief rundown of how you can come up with a preliminary size of a steel I-girder. Now I'm focusing on steel because when it comes to concrete, particularly precast and pre-stressed concrete, it's not really so much of an issue with sizing because you're just going, into the catalog of available shapes and picking the one that makes sense. So it's not as if, it's not, with steel it's a little more difficult because you have to actually come up with a tailored size for your girder. So I want to talk about that for a little bit. I want to talk about just some general fabrication aspects of steel I-girder bridge design that I think you need to be aware of. And just sort of closing the loop on that. Keep in mind when this is all said and done, I'm going to show you an example where we come up with a preliminary size of a girder. What we'll then do is take that preliminary size and do a boatload of calcs on it. Now those calcs, whether you're using MathCAD or using Excel or whatever software package that you choose to use, I'd argue that if you want a truly optimized design, software really is where it's at. Because what's going to happen is this. You're going to come up with a preliminary size, and then you're going to do all this math. Okay? And you're going to, when it's all said and done, you're going to see, okay, either this girder is over-designed or it's under-designed, so you're going to have to tweak the size. Okay? So let's say you have a big Excel sheet that does all these calcs for you. Well, if you change the flange size from, or flange thickness, let's say from 3/4 of an inch thick to 7/8 of an inch thick, it updates everything accordingly. So what I'll say is this, starting next week and probably for the next little bit, we're going to be talking about some fundamental bridge engineering calcs, and I would say that whether it's Excel or MathCAD or whatever software package you like to use, I would get familiar real quick, and yeah. I would say that, let me ask this for you design teams, have you started to put together or create like a group Dropbox or group file storage, things like that? Well, you're going to start using it real quick. So, but that won't be until next week. I want to sort of set the stage with this lecture. Okay. So one of the things I'll say about developing an initial girder size, or at least just coming up with the size of your girder, is if I give you a bridge and I say, okay, this bridge is 100 foot long, design the girder, not knowing where to start, just figuring it out, that can seem kind of daunting. If you're in design mode, what you're trying to determine, if we're talking about, let's say, a steel girder, you're trying to determine the geometry of your girder, how wide your flanges should be, how thick your web should be, so on and so forth. I'm going to show you a couple resources that'll make your life a little easier there, but I'm also going to show you some rules of thumb. You kind of need a girder size for a couple reasons. You need something to start with, to start doing some calcs so where you can begin that process of iteration. Here's a girder. Let's evaluate it and check it. Is it good? Is it bad? Do we need to tweak that girder size? But you also need some sort of preliminary girder size for the purposes of cost estimation. How do you know how expensive the steel girder bridge is going to be if you don't even know what the steel girder looks like? So that's sort of what I'm trying to cover in this. So I've mentioned this before, that by and large the best resource for estimation and preliminary sizing and the initial phase of your project is your firm or your company. They're going to have data on projects that they've been doing for years. And so usually you'll have companies that have developed things like span to weight charts, and they'll have just guides that they can use in-house to make sizing a lot easier. If you don't have that, and even if you do, I'd like to think that some of these rules of thumb I'm going to show you are pretty easy to use and can get you pretty close to the way there in terms of sizing a girder. Now, what did I mean by span to weight charts? A span to weight chart would be sort of something like this. So what we have here, and this comes from the National Steel Bridge Alliance. I have this posted on Blackboard, and that where it says website here, that's a link that will take you to their webpage. They've posted all sorts of design resources on the website, and this span to weight chart is just one example of one of those. So for instance, if you look here on the x-axis is listing the span length, and on the y-axis, it's listing the girder weight, and it's listing it essentially in a pounds per square foot. The idea is how heavy is this bridge per square foot. And so the cloud, the maximum and minimum is sort of the range. So for instance, if you're looking at a 200-foot span bridge, then your girder weights could pretty much be anywhere from here to here, and that red dashed line is sort of a trend line, something that you can use for prediction. I'll leave you to review that to your heart's content. I think it's probably a good idea that you all go to that website and check it out. We are doing a bridge project in here, so National Steel Bridge Alliance is probably a good resource. Yes?
Why would it be that different companies have different charts?
That's a good question. So why do different companies have different charts? I'd say that there's really two reasons for that. The first is just economics. Bridges in West Virginia just don't cost the same as bridges in Utah and Washington and Maine and whatnot. So I think local economics are going to play a big factor in that. And the other is fabrication practices. You can design a bridge, but ultimately somebody has to build it. And certain fabricators have certain preferred details and preferred fabrication practices and so on and so forth. So if you're working with this fabricator and you've been working with them for 30 years, well, you kind of know how they're going to fabricate things, if that makes any sense. Now, in the end, you are making a sort of indirectly a good point. In the end, the AASHTO spec doesn't change. It's the national spec, so it applies everywhere. So it's a good point. Excuse me. Any other questions? This is good stuff. Okay, so what I'm going to do is I'm going to talk to you and show you some rules of thumb that you can use to come up with a preliminary size. I'll go ahead and tell you that these equations aren't really things that can be derived. There's one that can kind of be derived, but most of this is based on experience. Most of this comes from designing hundreds and hundreds of bridges and figuring out what works. So we're going to go through these rules of thumb, and then we're going to use them to come up with an initial size of a girder. And so you can take that initial girder and you can compute all sorts of things. You can compute how heavy it is. You can compute the moment of inertia. You can compute live load distribution factors. You can compute all sorts of different quantities. And you'll probably need to tweak this girder size in the end. And that's where something like Excel comes into play, or maybe MathCAD or whatnot, because all you have to do is change an input value and everything else updates. So it makes your life a little easier. So really, when you're sizing a girder, you've got 6 variables, okay? So think, if you have an I-beam, there's 3 components to an I-beam, right? There's a top flange, a web, and a bottom flange, right? And so each of those plates are going to have a width and a thickness, right? So we're going to take each of these parameters one at a time and see if we can come up with a preliminary size for a girder or some rules of thumb. So let's start with the girder depth, okay? I start with the girder depth because by and large the depth of the girder will pretty much tell you how strong the girder is. The deeper a girder is, the stronger a girder is flexurally, the more bending moment it can withstand. Now, you can come up with a girder depth a couple of ways. If you open up the AASHTO spec, you'll see in Chapter 2, there's a table that lists traditional minimum depths of superstructure. So, for instance, if you're looking at a, let's say, pre-stressed concrete structure, and you're using precast I-beams, then a traditional minimum depth would be 0.045 times however long the bridge is, whatever the span length is. So if it's a 100-foot bridge, take 100 times this, and so that'd be 4.5 feet. So the girder would be about 4.5 feet deep. So you can use traditional minimum depths. You can also go off of rules of thumb. So traditionally I'm just showing you this for steel bridges, but traditionally the L over D ratio, so L over D is the ratio over how long the girder is versus how deep it is. Traditionally that depth is somewhere between 25 and 30. So a good first equation is let's just go halfway in between. So I've got a series of equations in this presentation. So this would be equation 1. So to start out, if I have a bridge that's 100 foot long, I can tell you pretty much how deep that girder needs to be by taking that length and dividing it by 27.5. Okay, and you're going to see these equations are pretty simple moving forward. Everybody okay with this? Okay. Okay, so the next thing I'm going to try and handle is the web thickness. So we got a top flange, web, bottom flange. Let's talk about the thickness. Okay. Now, in structural steel I-Girder design, if you have a web that isn't longitudinally stiffened, okay, and I'll show you what that means here in a second, but if you have a girder that does not have longitudinal stiffeners, what we call the slenderness ratio, the ratio between how deep the web is and how thick it is, that ratio has to be less than or equal to 150, and that comes straight out of the spec. Now, for our purposes and for design purposes, we're going to back that off a little bit, and we're going to use 120. That comes from experience. If you're at 150, you're sort of pushing the envelope a bit, but you do kind of want somewhat of a high slenderness value. To give you kind of an idea, the more slender a web is, as long as you don't have like significant buckling issues to deal with, it basically means you're using your steel more efficiently. So it's almost like the Price is Right. We want our slenderness to be close to a certain value without going over. So I would argue a pretty reasonable D over TW for design would be 120. So if I have the depth, I can come up with the web thickness pretty easily. Okay. Now that's our webs. Let's talk about our flanges, or that's our web. Let's talk about our flanges. Now, if you have an I-beam, you got two flanges. You have a compression flange. Now, if we're talking about a simply supported bridge, we have a compression flange up top. We have a tension flange on the bottom, right? Remember, take a beam, you bend it. The top's in compression, the bottom's in tension. Okay? So let's deal with the compression flange first. Okay, now there's a limit in the spec, and right out, let me say this. Like for where I say here, ASTRO requires the BF over D ratio be less than or equal to 6. I'm sure some of you are like, where the hell are you coming up with that? Don't worry, we're going to go through the spec in very significant detail. For now, just sort of trust me on where a lot of these limits are coming from, and we're going to go through it in due time, because you all are going to get to know the bridge spec quite well. We're going to look at, structural analysis issues with bridges. How do you handle live load distribution? How do you handle stage construction? How do you handle non-composite girder design? Composite girder design. We're going to, don't worry, you all are going to be familiar with this stuff when this is all said and done. Okay, so the limit is that your BF over D ratio has to be less than or equal to 6. For design purposes, I say let's back that off a little bit and use a ratio of 4. That comes from experience, and it gives us a flange that's a little bit more stocky, which pretty much is what we want. If you want to create the strongest girder possible, what you're wanting to do is take compact flanges and get them as far away from each other as possible. That's how you get flexural strength. So you kind of want flanges that are a little bit stocky, and you want them far away from one another. So I propose take D over 4 to get your compression flange, or your compression flange width. Now, the only one that we derive is the compression flange thickness, and this comes from a limit in the spec that prevents local buckling. So let's talk a little bit about local buckling. For those of you that are in steel design, we will talk about local buckling later on, and we will talk about it in very significant detail. But for our purposes in here, don't worry, we're going to talk about it in here as well. But I just want to give you sort of an overarching gist of what's going on with local buckling. I think the easiest way to explain it is to look at a column. So if I have a column, right, and I load it, you all are probably familiar with the concept of global buckling. The idea is imagine if I had like a yardstick in my hand, and I push and push and push, and the yardstick just sort of bows out, just suddenly goes, right? That's global buckling. Local buckling is if you have an I-beam, top flange, web, bottom flange, instead of the whole thing buckling, maybe it's just one of those plates, and they sort of crinkle. Let me see. Actually, you know what? I have MU Online right here. Let's see if I can pull one up from Steel Design. Let's see, lecture notes. Wait, nope, wrong one. Okay, this would be an example of what local buckling would look like. So you can see it's not the entire column that's buckling, it's just this flange or this web that's sort of crinkling. That's what local buckling is. And so if you want to prevent that, if you don't want that to happen, which more often than not we don't, full screen. What you have to do is you have to satisfy the following limit. You have to satisfy your flange slenderness being less than or equal to that limit, 0.38 times the square root of E over Fy. And so that's actually pretty easy to derive. All we have to do is solve for the thickness and just plug and chug. So if I'm using 50 KSI steel, the yield stress would be 50. E, what's E for steel? Say it again. 29,000, there we go, 29,000 KSI. So if I take 0.76 times the square root of 29,000 over 50, I can determine a flange thickness for if I'm using 50 KSI steel. And if I'm using 70 KSI steel, that limit just changes a little bit. Just so you know, just so you're aware, your flange thickness should be bigger than your web thickness. Usually your flange thickness is somewhere between 1.5 and 2 times your web thickness. That's not always the case, and especially if you've got flange transitions or you have a really funky girder with, you've got different cross sections and flange transitions that can change, but that's just a rule of thumb. So we have the tension flange. The tension flange, typically you're wanting the tension flange to be a little bit thicker. In a composite bridge, you've got the top flange in compression, but then you've got the deck in compression. So the concrete deck is actually helping you out in compression. You don't need as much steel on top of the girder as you do on the bottom. So on the bottom, your flange, your tension flange is usually a little bigger. And that's another thing that's a little different when you're looking at like plate girders, for instance. With plate girders, usually the flanges aren't the same size. They're different because you're tailoring each flange to a given demand. So your girder isn't doubly symmetric, but that's common. So to give you kind of an idea, let's take this example. Let's say I have a bridge that's 150 foot long. Okay. Now units. If a girder is 150 foot long, that's 1,800 inches long. Okay. So first off, the girder depth. If I take the length and divide it by 27.5, that comes out to about 65.45 inches. I, as a designer, will never specify a web depth that's 65.45 inches. I'd probably just say 66. So we'll say that girder is 66 inches deep. As for the web thickness, take the depth, divide it by 120. So you get about 0.55. Typically, you're expressing web thicknesses either in 1/8 inch increments or 1/16 inch increments. Since this is preliminary, I'd probably go with an 1/8 inch increment. So 0.55, round that up to the nearest 1/8, and that's 5/8 of an inch. Is everybody okay with that? All right. Flange width. So we're going to assume that the flanges have the same width for our purposes. So take the depth and divide it by 4. So that's 16.5 inches. I usually specify my flanges in even inches, like every 2 inches increments. That's just what I do. So I'd go with 18 inches. So that's the flange width. As for the flange thickness for the compression flange, since we're going to do 50 KSI steel, we will take the flange width and divide it by 18.3. So that's just shy of 1 inch, so we'll assume a flange thickness of 1 inch. And then for the tension flange, bump that up, let's say 50%, and then we get a flange thickness of 1.5. So it's really not that hard to develop a rough starting size for your girder. Okay, you really kind of need something to start with when you're doing a lot of bridge calcs, because what you're going to do is this. You're going to take that shape and you're going to, let's say, write an Excel spreadsheet to compute a moment of inertia, to compute a girder weight, to compute live load distribution factors. And then when it's all said and done, you're going to determine, is this girder, does it perform adequately or not? And if it's too small, then you're going to take these values and adjust them. But you need somewhere to start. You got to have something to start with. So hopefully you think that this is a pretty easy means of sizing something. I mean, again, this is a, phase 1. You'll need to iterate this to get an optimized girder in the end. Yes? That is an excellent question. And the short answer is it depends. The long answer is it depends on your span length. And I'm not going to tell you everything, because I kind of want you to do some digging on your own. But I'll say this. The steel manual lists rolled shapes, like a W40 by 149 or what have you. If you were trying to design a bridge that was, let's say, 300 foot long, and you were wanting to use something out of the manual, I say good luck. Okay? The facts are, if you have a bridge that's that long, nothing in the manual is going to be economical. Nothing. You are actually going to take a plate, weld it to another plate, and then weld it to a plate on one. You're actually going to create your own girder. Okay? Now, that's for a 300-foot bridge. For a 30-foot bridge, I wouldn't waste my time cutting and welding plates. I would just pick something out of the manual. So the question is, where's the cutoff? I ain't telling you. It's not. I don't have an answer for that. But I'll say this. Your span lengths in this class, you all are going from the 60s to the 120s. Y'all might be in that area, in that range where a plate girder versus a rolled beam is going to be, sort of the dividing line. I'm not telling you, because you need to do some research on your own. Now keep in mind, we're talking about steel with concrete. You're just basically sort of looking a lot of stuff up from standards. We're going to talk about some DOH standards later on. So, everybody good? All right. Let me talk to you a little bit about some layout considerations. So you all have a project where you have a bridge. You know that you've got, let's say, 2 12-foot lanes, 2 3-foot shoulders. How many girders do you need? Do you need 4 beams? You need 8, 6? How many do you need? So let's talk about laying out a bridge. And a lot of this is going to hold true for concrete structures as well. The actual values can change, but a lot of the general advice doesn't. So let's talk about girder spacing. In other words, how far apart your beams are from one another. Generally, wider girder spacing is more economical. Okay? In other words, if I could have 4 beams spaced at 10 feet or 5 beams spaced at 7.5 feet, I'd go with the 4 beams spaced at 10 feet. Okay? The reason why is, granted, each girder is going to be heavier. If you use less beams, those beams need to be bigger. But that means that there's less girders to fabricate. You only have to fabricate 4 of them instead of fabricating 5 of them. And if you have less girders, you have, let's say, less cross frames in between those girders. maybe the girder, the girders are a little heavier, and honestly, maybe your overall weight on the project is heavier. But it's less girders to fabricate, it's less cross frames, it's less girders to lift into place. Imagine lifting 4 beams into place versus lifting 8. More time on the site, more traffic interruptions, etc. Yes.
So are we considering load path redundancy and we're considering girders, like number of girders and spacing as well?
You're talking about 4 or more?
Yeah, like are we still following the typical like fracture critical standard?
Yes, yes. So let's talk about that because a lot of folks in here might not know what that means. So what she mentioned was a concept called load path redundancy. That's sort of a fancy way of stating what happens if you have a bridge and one of the main load carrying elements fails. Okay? So if you have a bridge that has, let's say, 8 beams, and one of those beams fails, yeah, it sucks, but you got 7 beams left over. And more often than not, designed properly, you'd think that they'd be able to pick up the slack. But what if instead of 8 beams, you only had 2 beams? One of those beams fails, that's a problem, okay? So what we have defined in the land of bridge engineering is a term called fracture critical, okay? If you ever are doing bridge inspections and you hear the term fracture critical, you go, oh no. And so some of you that have done bridge inspections know what I'm talking about. You have to spend a little bit more time and a little bit more effort investigating fracture critical bridges because if one of those main load carrying elements fails, you got some problems. Now, it's not super codified in the spec, but the way that the spec is geared and written, generally if you're using 4 beams or more, you do not have to worry about fracture criticality. So I'm going to give you one hell of a strong suggestion on your project and say you use 4 or more. Now, that's if you're talking about, let's say, a composite steel I-girder bridge where you have, a concrete deck and steel I-beams. If you have a shorter span and you want to use a hollow core slab or post-tension segmental boxes, the cross-section is different. So, we can discuss that when we get there. But that depends on what you use for your span. I'll say this. The longer your span, the beefier your cross-sections. Like if you've got the super high spans, you're probably not using like a hollow core slab. You're probably using some like ASHTO type 3, type 4s, something like that. So, but we'll get to that here in a little bit. Any other questions? This is good stuff. All right. A rule of thumb for girder spacing is that if you have spans less than around 140 feet, you probably need to be using around 10 to 11 foot girder spacing. I think that's pretty reasonable. Depending upon the width of your bridge, that might get reduced a bit, but that should be pretty reasonable. Now, the wider your girder spacing, the thicker your deck is, okay? Because think about this. You have cars driving on the bridge. Well, how does that load get transferred? Car goes to the deck goes to the beams goes to the abutments goes to the ground. So the concrete deck has to hold up the girders as well. And if you have these beams that are spaced really, really far apart, you need a really thick concrete deck in order to support that. So if you're using like really, really wide girder spacing, your concrete deck is going to get pretty thick. A very, very, very common concrete deck thickness for the types of bridges that we're talking about is 8 inches. Whereas if you're using really, really wide girder spacing, you might be going 9, 10, or even higher. So, and we'll talk more specifically about stuff like that and sacrificial wearing surfaces and things like that later. All right. Now, wait. I don't know what happened there because that's the same slide. I don't know. Let's talk about plate thicknesses. Here are some general minimums to go off of. Like, I don't want to see anybody specifying a girder that has a plate thickness at 1/8 of an inch. That's bad, okay? And it's bad not from a load carrying standpoint. It's bad from a serviceability standpoint, from a day-to-day usage standpoint. What happens if you have a bridge that's outside, you know, for 75 years, and you're using plates that are only 1/8 of an inch thick. What do you think is going to happen? It's going to corrode. It's going to rust through. And then even if the plate has adequate capacity, it just doesn't perform well from a realistic perspective. So plate thicknesses, generally, if you're looking at webs or you're looking at stiffeners, 7/16 inches is a usable minimum. With flanges are usually 3/4 inches or more. So if you're specifying a flange that's, you know, 1/2 inch or something like that, you're probably doing something wrong. Okay, so your flanges should be the beefier elements in your design. So one thing about specifying plate thicknesses and plate sizes, you as the engineer might want to get super precise and go, I want to use a 64th inch thick plate that is super tailored and it's performing beautifully. Now go try and buy a 19/64 inch thick plate and see how commonly produced that is. So 7/16 inches is a minimum, but I'd say 1/2 inch is preferred because the mills are rolling 1/2 inch plate all day, every day. The more esoteric your plate thickness, the more rare, the less commonly available it's going to be. So just keep that in mind. Even if your girder's getting a little heavier, look, if your plate thickness is going up 1/16 of an inch, I doubt you'd notice it at the end of the day when you're tallying up the final cost of the entire project. So it's just something to think about. Plate availability, I mentioned NSBA. ASHTO NSBA collaboration documents have some pretty good info, and I screen captured one here just so you could look at it. Again, I highly recommend you go to that website and check it out. But for instance, if you have a 1/2 inch thick plate, for instance, it'll tell you, if you're looking at, let's say, 1/2 inch thick plate, what are some commonly available sizes. So you can buy, let's say, a 96 inch wide plate that's, let's say, 972 inches long, and then you can cut flanges out of it, you know, and then that can be your flanges for your girder. So, does that make sense? Okay. Flange sizing, okay? One thing that you will find when you're trying to optimize your design is that the actual size of the flange, more often than not, will change along the girder. That's very, very common, okay? What I suggest and propose to everybody in this room is that if you're changing the size of the flange along the girder, that's great. Because here's kind of the idea. What's a moment diagram look like for, you know, if you got a simply supported beam and it's just a distributed load? It sort of goes like that, right? So the biggest moment's in the middle, right? You don't have much bending moment on the ends, right? So do you really need this super thick flange in the at the ends? Maybe at the ends you can use a flange that's a little bit thinner. You can use the thicker flange where you need it, right? And you can shave some serious weight off the girder, okay? My advice to you is that when you're transitioning your flange sizes, transition by thickness. Don't transition by width, okay? Because what'll happen is this. You know, let's say you have, let's say a 3/4 inch plate, a 3/4 inch plate, and this is 1 inch. What you can do is you can take a big, you know, standard mill 3/4 inch plate, a standard mill 3/4 inch plate, and a 1 inch plate. You can weld the whole thing together and then just plasma cut strips out, and then now you've got your flanges. Take those flanges and, you know, weld them to your webs, and then there you go. But if you make the flanges, instead of making them thicker, if you make them wider, you can't really do that. What you have to do is you have to cut these, cut these, cut these, and then take those pieces and combine them together individually. And it's a pain in the butt. So, does that make sense? So don't do that. Just change the thickness. Don't change the width. There are fabricators and bridge engineers out there that are still changing the width, and it's a little maddening sometimes. Well, did I have it? Oh, that's it. All right. I was like, why is it not working? Oh, that's why it's not working, because I'm done. Any questions?
Would the thickness still like change if there was like, say for example, 2 piers in between the abutments?
It can. Yeah.
Like they're corresponding?
Yeah. Oh, yeah. You can, if you have, let's say, interstate overpass. And so there's multiple piers, and then the whole bridge is something like 400 feet long. You could have 7 or 8 flange transitions along the whole of the girder. Now, you're usually trying to exploit symmetry and make it, make reasonable sense. But yeah, the idea is this, is that if you can save some serious weight, you can save some money. The old adage is that if you can save 1,000 pounds of steel, like, go with the transition. If not, don't worry about it. So okay, let me see if I can use the pen. Whoop. Hold on. I may not be able to draw it out, but we'll see. Let me see what I can do. Okay, so I'll try and explain it verbally. So you have an I-beam, right? And you recognize that the flange in the middle probably needs to be bigger. I propose make it thicker, okay? Because what you can do is this. Okay, so let me see if I can go here. Okay, all right. Let's say you've got your girder and each flange is like 20 inches wide, okay? What you could do is you could take a standard mill plate. Standard mill plates are pretty wide. They're like 96 inches wide, 120 inches wide. They're really big. So what you could do is you could take a standard mill plate, standard mill plate, standard mill plate, weld the whole things together, and then just cut, bam, there's your flange. Cut, there's your flange. Cut, there's your flange. Whereas the only way that works, though, is if you're transitioning the thickness, right? Because it's the same width here as it is here, it just got thicker. So you just cut, and there you go. Whereas if it's all the same thickness, but you change the widths, what you're having to do is you're having to cut this plate into pieces, cut this plate into pieces, cut this plate into pieces, and then like Lego blocks, sort of arrange them in your fabrication plant. That can take a lot more resources, a lot more space in the fab shop. It can take more time, and it ultimately is more expensive, so don't do it. But did that make sense? Yeah. So don't do that. So, don't do that. Sound good? All right. Just so you are aware, starting Monday, okay, we are going to do some pretty significant delving into bridge engineering. And so what I mean by that is we're going to start talking about section properties and DC loads and the spec and live load distribution. So it's probably not a bad idea if you have a laptop to start bringing it, because we're going to be doing some calcs together. Was the spec, did it open for everybody? Because I had gotten an email where somebody was having some issues opening it and they weren't alone. Where are we at with that?
So when you click on for whatever reason, when I clicked on the spec book, if I didn't touch anything, it would load. But if I tried to scroll too soon, it just quit loading it.
It's the file size is huge.
It's a big,
So I just saved it to my computer.
Yeah.
That's what I did.
So
but that did it?
get it to load, don't touch anything.
Yeah.
It's like 700 or like 1700 pages. Let it load it and save it to your desktop.
We're not using all of it. So don't. We're not using all of it. Don't worry. All right. I guess I'm going to call it for now. Forgive me if I've been loud, but I'm not really feeling very well today. But we're going to start back up on Monday, and we're going to take a deep dive into bridge engineering starting Monday. So that's all I got, everybody.